So let's take a look at doing math with units. We call this dimensional analysis, and dimensional analysis is a powerful way to make sure that we are paying attention and doing things right when we're doing equations. And I'll show you a couple examples of that. First, let's get started here. The basics, we take meters plus meters, we end up with meters. Now, I don't want you to think, oh, that's 1 meter plus 1 meter equals 2 meters. This is true. 1 meter plus 1 meter is 2 meters, but all we're looking at here are the units. If I add a meter and a meter, what I'm left with is a result that's still in meters. I add a distance plus a distance, I still have a distance. Same is true with subtraction. If I take a meter minus a meter, I still have a unit in meters, I still have a distance. This is a little bit different. If I take a meter times a meter, that's a meter squared. Okay, this is a distance times another distance, but it doesn't give me a distance anymore. This actually measures an area. A square meter is a measure of area. Now this case is a little bit different. A meter divided by a meter, this is actually a unitless measurement. And that happens when a measurement's a ratio. Like on the unit circle, if you measure an angle, you can measure it in radians. And the radian, the measure of this angle in radians, is actually a ratio of the arc length, this distance right here, we call that S, and the radius, S to R, that equals theta, and theta is in radians. Well, this is a measurement of distance, this is a measurement of distance, so these meters cancel, and that gives us that angle measure. So it's a unitless measurement. It has no dimension. Now, when we start getting into a little bit more tricky things where we have derived units that we're messing with, then you have to pay extra special attention to what's going on. So this is a kilogram times a meter divided by a second divided by a second. So I have to rewrite this just to make it make sense in my head. So I have a kilogram times a meter divided by a second, and then I'm going to take that whole thing and divide it by seconds again. So all over seconds. But remember, that's invert and multiply. So this is seconds over 1. So instead of writing it like that, I'm going to write this as times 1 over seconds. So this gets me a kilogram meter per second squared. Okay, so seconds times second is seconds squared. And if you recall earlier, I told you this was a Newton. So that's how you deal with that when it's like this. Now this one's a little bit different. This is a kilogram times a meter per second squared times seconds. So now I have a kilogram times a meter over a second squared times a second. Well, this is seconds over 1, so this second cancels that square, and I'm left with a kilogram meter per second. Or if you'd like, kilogram meter per second. Okay? So you treat these units as though they're algebraic quantities, and that's pretty straightforward. Now, we can use dimensional analysis to check to see if our equations that we have are actually valid. Valid means that the equation makes sense, and that if we're saying that this side of the equation is equal to this side of the equation, they better measure in the same unit. It doesn't make sense to say force over area equals density times the acceleration due to gravity times height if this one ends up measuring a meters, a distance, and this one ends up measuring a force in newtons. If the units don't match, we know the equation is wrong. If the units do match, the equation is not guaranteed to be right, but we'll know for sure that at least our unit part of it makes sense. All right, so we want to check to make sure that this equation is valid in that the units on the left match the units on the right. And so down here it tells us what all these things are. It says force is measured in kilogram meters per second squared. So I'm going to replace my F with that unit, kilogram meter per second squared. And then it says divided by area. Now I know divide by area is the same as invert and multiply. So instead of writing this as over meters squared, I'm just going to go ahead and multiply it by 1 over meters squared. That lets me keep track of my units. And that takes care of this side of the equation. Now I'm going to simplify. Meters over meters squared and 1, so I'm left with kilogram. This meter cancels that square. So kilograms over seconds squared meters. Right, now that's an interesting unit. It's actually got its own name. It's called a Pascal, but we won't get into that. And then rho. This is actually the Greek letter rho. It means density. So I have rho, kilogram per meter cubed, times g, the acceleration due to gravity, which is measured in meters per second squared, times a distance h, which is measured in meters, and this would be meters over 1. So let's see, I have meters times meters, which is meters squared, which means this meter and this meter are going to cancel 2 of these, and I'm going to be left with just 1. So this is a kilogram meter second squared. Are these two units equivalent? Absolutely. This one says second squared meters, this one says meters second squared, but it doesn't matter. That multiplication doesn't matter what order we go in. So yes, these two units are equivalent. So force divided by area does have the same units as density times the acceleration due to gravity times height. Another example, check the validity of this equation. Well, this equation is actually the radius of an inscribed circle in a triangle. So if we have a triangle that has sides A, B, and C, of lengths A, B, and C, S is actually the semi-perimeter, or A plus B plus C divided by 2. And this gives us the radius of the inscribed circle, or the circle that touches is tangent to all three sides. So it says the units of all of these things is meters because they all measure length. So do we have meters when we're all done? Well, right here I have R, which is definitely meters. So the left side of this is length. Now S minus A, which is a meter minus a meter, that's right, we're just looking at units, we're not looking at values here. So a length minus a length gives me another length. So I do have a meter for that. S minus B, again, a meter for that because it's the same argument. S minus C, a meter for that. And then S, which is still length, is also in meters. So this meter will cancel one of those meters and I'm left with square meters. Okay, but this is all under the radical, which means square root that. So if I square root a square meter, I'm left with just a linear meter. And so I do have meters on the right and meters on the left. Similarly, kind of doing the same thing, we can figure out what units would be. So determine the units of A in the equation V equals AT. If you know that V is measured in meters per second and time is measured in seconds. So I'm going to replace my variables with their units. So I have meters per second is equal to whatever the units of A are times T, which has units of S. So instead of T, I'm going to write S. And then I want the units of A, so I'm just going to solve for A, divide by S, divide by S. Now be careful when you divide, that's S over 1, so that's invert and multiply, so I have meters per second, which is also a meter per second squared, is the unit of A. Okay, so meters per second squared is a unit of acceleration. So that tells me how much faster something gets every second. Another example is determine the units of g in this big long equation. So I have v equals the square root of 2gm over x. V has units meters per second, so I'm going to replace my variables with their units. So meters per second is equal to the square root of 2, which is a number. It doesn't have a unit, it's just a constant. I don't care about it, I'm ignoring it. G, which is actually what I want to know, m, which has units of kilograms, divided by x, which has units of meters. Now this is messy because I have this radical over here, so I'm going to square both sides. So square this side. If I do it to one side, I do it to the other, square. Now, when I square a fraction, remember that's square top, the numerator, and the bottom. So meters squared per second squared is equal to, and now my radical's gone, g times kilograms over meters. Now I just want g by itself, so I'm going to multiply by the inverse, meters over kilograms, times meters over kilograms, and this meter cancels that meter, this kilogram cancels that kilogram. Meters times meters over here is meters cubed, and kilograms seconds squared in my denominator. That is the unit of g, the universal gravitational constant. So just pay attention to your units, make sure you're doing your fraction math right, but this is pretty straightforward.